Okay, today we're finally at our last way that we're going to multiply two vectors together or find the product of two vectors. This one's called the cross product, okay? And the cross product is a product between two vectors that comes up with a third vector, another vector. All right. Um, the interesting thing about the cross product, it is used a lot out in the real world somewhere. Rotation, electromagnetic field situations, you'd have the cross product. Torque is a cross product thing. You've heard that word before as well. So there's a lot of applications to it in the real world of what this cross product is. All right. So basically, the first thing that we want to take a look at first is what is it? How do we define it? Okay, with vectors. Okay, now we write the cross product with this x in between. It means specifically this cross product. We know that it's a vector. Okay, by definition, it's a vector, so it has both a magnitude and a specific direction. Okay, that we use by convention. So by definition, this is the geometric definition of the cross product. The magnitude is equal to the area of a parallelogram formed by the sides of the two vectors themselves. Okay, so first of all, just take a look at the diagram itself. We have a vector A, we have a vector B. They are set up tail to tail again. Okay, we have the theta between them, and it's defined the same way as it always has been. The vectors tail to tail, we have the smallest angle in between them. Okay, since this is the cross product is defined to be the magnitude, or the magnitude is equal to the area of the parallelogram. All right, the area of a parallelogram is the base times the height. Now, in the diagram, you can see that the base is the magnitude of A, all right? But what is the height? Okay, if we take a look at the height of the parallelogram with this smaller triangle on the left-hand side, a right triangle, okay, you can see that the height is opposite. It's the opposite side of theta. Okay, B would then be the hypotenuse, and the magnitude of B is the hypotenuse. Opposite over hypotenuse is sine of theta, so we're using the sine theta. So we end up with that the height is equal to B times sine of theta. Okay, the magnitude of the cross product is the magnitudes of both vectors being multiplied together times the sine of the angle between them. Okay, it looks almost the same as the geometric dot product, except the dot product used cos theta. Okay, cross product uses sine theta, so you remember that part. All right, now the direction. The direction simply is done by what's called the right hand rule. Okay, so we know that it's going to be perpendicular, all right, to both of the vectors that it's basically designed from. So it's going to be, in this case, either coming out of the page or into the page, all right, because it's perpendicular. If the page is the flat surface that A and B are on, all right, then you're either perpendicular, it's either coming up or it's coming down. All right, now it satisfies the right hand rule. What I've done is I showed you a very quick video here. You can take a look at it, at this explanation of what the right hand rule is. So here's what you do. When your fingers of your right hand point in the direction of A, which is the first vector, and it curls towards the direction of B, then your thumb points in the direction of the cross product. Okay, so I can't show you here examples on the board, so that's why, again, I gave you another video that you can take a look at. Okay, so if you need to, stop it and take a look at it now, and then you can come through. All right, the reason why that we've waited until now in order to use the cross product is because it only works in 3 dimensions. All right, so Let's take a look at a couple of examples. This is geometrically, all right? And we'll see what we can do with these. So first of all, if we have the following vectors A and B, you can see them lined up the way they are right here, all right? We've got, what we want to do is determine the direction of the cross products and the magnitudes, okay? So what we have, we've given the magnitude of A is 4, the magnitude of B, vector B is 5. We're going to state that theta is 60 degrees. Okay, well, we can do the magnitudes first. It's quite easy to do the magnitudes of A cross B, 4 times 5 times the sine of 60. All right, and so you'll end up with your 10 root 3. In the first case, we're saying that the direction is out of the board. All right, if you look at the right-hand rule, and what I'd like you to do is, I want you to actually do it on your screen right now. Put your right hand, okay, your fingers across A in the direction of A. Theta is in the palm of your hands. Curl your fingers up, and your thumb is going to be facing out of the board. So that would be for A cross B. We've got a magnitude and direction. For B cross A, the magnitude is identical. We know this because for the magnitude, we're dealing with scalars. So instead of 4 times 5, it's just 5 times 4, then the sine of 60. So you're going to end up with the exact same magnitude. However, since B is listed first here, take your right hand. Put your right hand on B with the fingers according to B. The theta is now in the palm of your hands. You curl your fingers in, your thumb is pointing into your screen or into the page, right? So this is what you have, right? Into the board, into the screen, all right? You notice that the commutative property does not hold true for the cross product, okay? You have the same magnitude, but opposite directions. So therefore, these two vectors are not the same. They're actually the opposite vectors because it's opposite. All right. Now, I mentioned in a previous lesson, when we're going to look at the angle between two vectors, we normally look at the dot product, and that is going to be true. The normal way of doing it is looking at the dot product. However, when you're given the cross product or the magnitude of the cross products with the magnitudes of the others, then just go ahead and take a look at dealing with the angle with the cross product itself using sine theta as opposed to trying to figure out cos theta. You're already given the magnitude, okay? So you have this. If you're given maybe the cross product as a vector itself, then you know you can figure out the magnitude of that cross product. Then you use this one here, okay? All right. So this would be the only case where if you're looking for an angle, if you're given the cross product, whether it's the actual vector components itself or you're given the magnitude of the cross product, this is when you would use the sine theta as opposed to the cos theta with the dot product. Okay. Quick thought process here. If you've got the magnitudes of the two vectors and the angle between them, can you determine the cross product? No, you can't because you don't know the direction, right? So this question stems from here. You're given the two magnitudes, right? You could figure out what the angle is, but you don't in fact know what the cross product actually is because you won't have the direction of the cross product. It could be into the page or out of the page. Okay, so there's your summary. Okay, cross product, brand new today. We've got our definition. This is our geometric definition. Okay, again, everything is lined up tail to tail. All right, the direction follows the right hand rule. Some of you may know something very similar to this with in physics using, you know, your thumb and your pointer finger and middle finger. right? This is the right-hand rule. It works out the same way. All right. In the next lesson, we are going to work out the cross product, what it is algebraically. If we're given the algebraic um, vectors, how can we determine the cross product? And that will be the next lesson. Okay, so for today, we've got a couple of lessons or work questions in your textbook, the online version that we have, and also some extra ones here that I put down. They're really good ones, I think, uh, from a different textbook. So I figured I'd give them to you here. Okay, good luck.